Okay.
Got it. Okay.
Okay. So thank you very much for this opportunity to speak. Yes, so I'm going to talk about the gravity dual of complexified SYK. So this is the work we have been doing in these 3 papers in collaboration with Antonio Garcia, who is in Shanghai, and also 2 of his students in the last paper. So first of all, let me recall what is the SYK model. So the SYK model is a simple quantum mechanical theory involving n Majorana fermion with all-to-all interactions, so given by this Hamiltonian. And this theory is very interesting because in some semi-classical regime involving large n, it is holographic dual to JT gravity. And this segment, so JT gravity is a 2-dimensional gravity with ADS2 boundary conditions. And so this is the toy model of ADS-CFT. And here the duality just means that it's just the statement that both theories are described by the same effective action in this semi-classical regime. And so this toy model of ADS-CFT has been very successful. So for example, it has led recently to better understanding of quantum black holes and the gravity path integral. And so here, today we will ask the following question. So now what happens if you complexify this SYK coupling, so the GIJK? And I will explain later why you would want to do that, but here, let me just tell you the results. So if you do that, so if you add an imaginary part, for example, and here, so this coupling is supposed to be random, so you're supposed to average over it, and here you will average over both the real and imaginary parts. And actually from the Hamiltonian, you can see that this is just a deformation by a marginal operator. And using the usual ADS-CFT dictionary, this corresponds in the bulk to a massless scalar field. And indeed, we will see that this complexified SYK is dual to JT gravity with a massless scalar field in the bulk and with these boundary sources corresponding to this marginal deformation. And I will show that this model is actually pretty useful to study some aspect of the gravity path integral. So here I want to think of JT gravity really as some kind of semi-classical approximation of SYK. So in the same way, for example, supergravity is viewed as a semi-classical approximation of unequal post-Poisson-Mills. And I'm really interested in higher dimensional ADS-CFT, but this is a simple toy model where hopefully we can extract lessons that would be applicable more generally. So indeed, the motivation for me is the gravity path integral, and what I can say about it is that, you know, despite many successes and many recent discussions, it's still rather mysterious. For example, there are these 2 questions that we want to address in this talk, in this model, which is, you know, it seems that the gravity path integral should be sort of some kind of average, but it's not clear over what. And it's not clear also what is the gravity without average. Another question is about how do you even define the path integral? So what is the contour of integration? And here I want to contrast what I'm going to discuss about with another story, which is the Sachenko-Stanford story, where JT gravity, where the path integral of JT gravity, or pure JT gravity, is dual to a random matrix model. And so in this case, they were able to actually compute the exact path integral. But this seems to be something rather special, because in higher dimension, for example, the path integral doesn't converge. So it seems that you can only define it as a sum of saddle points, which is not what they did. And from this perspective, you know, this theory of JT gravity with a massless scalar or any kind of matter actually is more realistic because it didn't, in this case, the exact path integral is also divergent, and so you should think of it as a sum of saddle points. And in our particular model, these complex sources will allow us to construct many interesting saddle points. And moreover, since we have this microscopic description in terms of SYK, this complexified SYK, it's actually a great model to study these wormhole effects in the gravity percent table. Yeah, and also I want to say, feel free to interrupt and ask questions. I'm also happy to make it more like a discussion. and yeah, so this is the main motivation, and now I'm going to jump into the construction of this wormhole and what we can do with this model. So before that, if you have any question about this, feel free. Yeah, so to recall, so this is the model we have. So it's just JT gravity with a massless scalar field, and this will allow us to construct this type of solution, this wormhole solution. Well,
sorry, I have a stupid question. So when you make this complex, the coupling complex, is it different from having the fermions, Dirac fermions, or is
it? Oh yeah. It's actually quite different. So
okay, yeah.
There is another. Yeah, actually, it's a bit confusing because there's another model called the complex SYK, where you just make this Majorana fermion into Dirac fermions.
Okay.
And this has been studied also. It's basically JT gravity with a U1 with an additional U1 gauge field.
Mm-hmm.
But this is not what we're doing here. And actually, as I will explain, like this complexified SYK is a bit different because, for example, the Hamiltonian is not Hermitian anymore. So we are studying a non-Hermitian theory, but basically we are going into the complex domain. We are complexifying things, and this is something that we know is sometimes a good idea in physics. And here I want to convince you that it is a good idea, because by doing this complexification, we'll be able to construct, for example, this type of solution which cannot be constructed otherwise, at least not easily.
I see. Okay.
So
thanks.
Yes. So if you want to have such a solution in JT gravity, so okay, I'm not going to write down all the equation of motion for the dilaton, etc. But one easy way to see that actually this is not a solution is just by computing this unshell action in terms of this variable b, which is the size of this circle in the middle. And you can see that this unshell action doesn't have a saddle point for b. So basically the wormhole will tend to shrink, and there's a divergence at b goes to 0, and there is no saddle point. But okay, so now you can see that the solution to this is just if you make this boundary sources imaginary, then there is a minus sign here, and then there will be a solution. And so this is actually what we're going to do. So if you pick this imaginary source to be pure imaginary, then the scalar field has a linear profile in the wormhole, and there is actually a solution. So how to think about these imaginary sources? So of course it's not a physical setup in the sense that, but it should be thought as the analytic continuation of a physical setup. And okay, this will be more clear when I explain also the SYK side. But here, just think of it as we're just allowing this KL, we analytic continuing this KL and KR, and when they are imaginary, there are actually saddle points. And then the saddle points are pretty simple. You can just solve for B here, and you can find that the unshell action is constant, so the free energy is constant. And what is interesting here is that there's a competition with the other saddle point, which is two black holes, which has this free energy. So, and what will happen is that at low temperature, there's a phase transition between these two black holes and this wormhole. And the critical temperature can be also computed. So this is the story here.
Can I ask a question before you go on? So you were saying that you have an exact expression for the chi field that supports the wormhole? Okay.
Yeah.
All right.
Yeah. So actually, it's very simple here. It's literally just it's just I cat times rho times the constant. It's just linear in this variable rho, because the equation of motion for k is just box k equals 0. So in these coordinates, which are conformally flat, the solution is just chi proportional to rho.
Okay. Thanks.
And so, yeah. And on the SYK side, what we're doing here is we have two copies of the SYK model, so two boundaries. And the Hamiltonian is the sum of these two copies. And so on each side, we'll add this imaginary parts with an opposite sign, because this corresponds to the fact that the sources here are IK and minus IK. And again, this is just some details about how we do the average. And then we can compute this, the crunch free energy. So we can compute the free energy of this, which is just log of trace E minus beta H with this Hamiltonian. And this is the advantage of SYK, is that it's simple enough that you can just compute it numerically. And so that's what we did. And so here we can plot the free energy as a function of the temperature. And so in gravity, what we have is we have these two regimes where we have the wormhole at low temperature and the two black holes at high temperature, because the dominant solution is the one with lowest free energy. And in SYK, we see exactly the same thing. So this is the first kind of evidence that this duality really works. And of course, this plot is more like a qualitative comparison, but you can also do something more quantitative, because you can compute this critical temperature and the energy gap on both sides, actually. And they both have this same scaling with K. And ultimately, the reason that this works boils down to the fact that both systems are described by the same Schwarzschild action. So, like at least so for the wormhole, this is the Schwarzschild action. And the only thing you need for this duality to work actually is that both in the JT side, you need the imaginary sources to lead to this contribution. And in the SYK side, you need also the imaginary parts to lead this contribution. And this is something that, although we cannot derive from the SYK side, it's very believable simply because this is basically the only imaginary operator you can write in this Schwarzschild action, and we expect this deformation to be marginal. So it's more like an effective filtering reasoning here. But so okay, yeah. So this is the first story, that we have this Euclidean wormhole that we can see both in JT and SYK. So is there any question about this? Okay. So now that we have this this interesting Euclidean wormhole, we can ask more difficult questions. And so one of the questions that has been discussed recently is the factorization puzzle. So this is the point that this is the observation that connected contribution to the path integral seem to be inconsistent in ADS-CFT because they led to this factorization puzzle. Namely, the product of 2z doesn't seem to be a product itself. So here, it's actually not a problem, because since we have a disorder average over coupling, then it's okay to have this difference being non-zero. Oh, sorry, there's a typo here. This should be like average of z times average of z, of course. But the puzzle is still there, because in some sense, the disorder average is something we do for convenience. But if we consider SYK as a single realization of the coupling, this theory also should have the same semi-classical low energy description, and the wormhole seems to be present there also. For example, if you compute the free energy of a single realization, so here it's average over 45, you basically get the same curve. It's going to be a bit more wiggly, but it's basically the same. But here the idea is that, so how is it possible that this wormhole contributes in a single relation of the coupling? It's inconsistent because of this factorization puzzle, and the answer here will be that you need to add some new saddle points known as half-wormhole. And this is an idea that was proposed by SYK, Sanford, and Yar recently. And what they did is basically to look at the SYK model, but a simpler version of it, where you fix time, because, just because they needed to be able to do the computation. And so if you do this, then you can look at the SYK model at a fixed relation of the coupling, and and see what kind of saddle points you get there. And basically what they showed is you have this half-wormhole saddle points that explain how factorization is restored. But one drawback of their analysis is that they were only doing it in the SYK side, and so that they didn't have a real gravity description of this half-wormhole. And so here in our model we'll show how to get such a gravity description. And we'll be able to see on the gravity side how they resolve this factorization puzzle. And so the idea is pretty simple. Basically, what you do is you just add some kind of end-of-the-world grain at this geodesic boundary. So this is the trumpet, so-called trumpet geometry. So these are the boundary conditions you put, and the scalar field here is important because basically what you're going to do is to put some arbitrary profile for the scalar field on this geodesic boundary here. So we can call it J of tau at rho equals 0, so in the middle. Well, J of tau is a fixed function on this circle. And so then you can check that this is actually a solution of JT gravity. And for this, it's important that you actually have this imaginary source here. So this plus means that we have this plus IK source. And for the same reason that, I mean, it's not, yeah, we will consider the situation where we have this source, with these sources. And then, yeah, so I will spare you the details, but basically you can compute everything. So you can compute the on-shell action of this solution, which will depend on, of course, the choice of this profile J of tau. And you find the saddle points. And you can also compute the one loop prefactor. I mean, you can do, the nice thing about this is that everything is one loop exact, and you can actually compute this one loop factor. But now here's the idea. So basically the idea is that the average over SYK coupling, so over this GIJKL, is going to be dual to the average over this boundary condition J of tau. So basically what you do here is that you're defining the model with a fixed boundary condition J of tau, and then you can integrate over J of tau you can average over J of tau in some ensemble. So for example, here I'm taking the measure E minus S, where S is some functional of J. But of course, there are many ways to do this. I'm just giving two examples. And so here, for example, I'm plotting a typical relation of J in these two possible ensembles, but of course, there are many possibilities, just to show that J of tau typically will be a very complicated function. And so this is how you encode these complicated features of the SYK coupling.
Sorry, I'm confused. Can I ask a question?
Yes, sure.
So, well, naively, I would expect when you do an average, the weight, the S, should be what's given, for example, by the on-shell action of in the holographic setup. In any case, I don't understand why you can choose different. I mean, you can choose different ensembles.
Yeah. No, yeah, totally. So this is right now I'm defining procedure, and I haven't shown that it gives the right gravity path integral as we wanted to define. But this is something that will be true at the end. But of course, here there are some arbitrary choice, and the idea is that it will be only true in some specific limits. So, for example, the limit has to be where you take this J to infinity, basically. But the important thing here is just to give a picture basically of what happens if you don't do the average in SYK. But this will be clearer when I know it's probably not very clear now, but I think it will be clearer when I explain how the correspondence works.
Okay.
So actually, so basically the way to think about it maybe is the following. So it's the fact that the idea here would be that the gravity theory where you have half-wormholes but no wormhole is dual to SYK at fixed couplings. And averaging over the J of tau is the same thing as averaging of the SYK couplings. So maybe to make things more clear, there are two gravity theory here. There is one that you might call the simple gravity theory, and this is, let's say, the usual semi-classical gravity where you just do the usual path integral and the sum of the saddle points. But here, what we are defining in addition to that is what you can call the exact gravity theory, where you add these half-wormhole saddle points with some arbitrary J of tau. And yeah, basically this is, and then what we want to show is that if you average this exact theory over J of tau, it becomes the simple gravity theory. But of course, here, there is many ways to do the average, as I explained here. So it's only true in some specific limits when this average becomes uniform in a way, but I will explain this. But of course here, we don't know what is the exact dual of SYK. So this is just a semi-classical approximation. And so this duality between this half-wormhole solution and SYK at fixed coupling is not going to be exact. But what we want to argue is that it's a good picture and it's a good approximation at low energy. So, and this is something that, yeah. So first of all, let me talk about the gravity side. So on the gravity side, the point is that this half-wormhole will average to 0. So there are non-self-averaging saddle points, which is also expected from the SSSY analysis. But if you take 2 of them and you average over J, then you get the wormhole. And okay, so and actually, what is interesting here is that if you want this equality of the average of the 2 half-wormholes to be exactly the wormhole, you need this is actually an exact equality, including, let's say, the one loop factor. So it's like exact at the level of the saddle point approximation. If you choose some specific average. So this is how the average is picked. So the average should be whatever you need for this to give exactly the wormhole. And once you have this, then this gives a resolution of the factorization puzzle in the same way as SSSY. And the way to think of it is, for example, if you consider like this Z minus Z plus, so you have one boundary with a minus IK source and one boundary with a plus IK source, then this is actually a product. So it's a product. So it does factorize in the exact theory, simply because it's like the 2 saddle points are the disk and the half-wormhole. And now if you expand this, you get 4 contributions. But now if you take the average of this, these 2 contributions will average to 0 because this half-wormhole is non-self-averaging. But this contribution, where 2 half-wormholes with the same J, will give the wormhole. And this is how from this exact theory, which does factorize, you get, after doing the average, the simple gravity theory where you have the non-average contribution. So where you have both the black holes and the wormhole. And this is the mechanism that was already explained in SSSY, but here we have a real gravitational description of it, I would say. And yeah, so of course, to get this, you need to take the average in the right limit. And now I will explain why this works. So actually, there's a very simple way to understand why this works. And it's just about, it just comes from the path integral, actually. So the point is, if you do the path integral over all geometries as a sum of all geometries, and then integrate it, you have to integrate also all fields on these geometries, then what you can do is you can do the path integral in 2 steps. You can first, let's say, integrate the scalar field, let's say, over the full wormhole here. So you integrate it over the full wormhole here. But you can leave the integration over the value on this circle for the end. And so this is how you can write the path integral as the integral over the j of tau. You can do the integral over j of tau at the end, and this integral over j of tau is then interpreted as this average. And so this is why this works. That it's just about a different way to. It's just about doing the path integral in a specific order, where you first you leave the integral over j of tau, so over the value of the scalar field at the geodesic boundary for the end, and you interpret it as an average. And this is also why I expect this to work in higher dimension, because it's simply based on doing this path integration in a different order. But now, so this may be like a bit yeah, yeah, and then this is just to connect with the SSY story, that you can also write this pair of half-wormhole as the wormhole plus a linked half-wormhole, and this is actually how you define the linked half-wormhole. So yeah, this is just to connect with their way of describing the. I mean, one other way of defining the setup. So basically, in the fact, yeah. So in the exact theory where you have factorization, it's either you have half-wormhole and no wormhole, but you can also keep the wormhole, but you have to add this linked half-wormhole. But it is equivalent. And now, like you can also look at the free energy of this half-wormhole. So if you have one boundary, like you have two contributions to the free energy, this disk and this half-wormhole. And what's interesting here is that, of course, the free energy is complex here, and then the real part is basically the same as this wormhole free energy. So you have this phase transition, which shows that in this regime, the half-wormhole dominates. But the imaginary part has this interesting pattern, which is like a saw pattern, that we can understand actually just from the sum of the saddle points. And then you can do the same thing in SYK. So in SYK, what you do is you add this imaginary part, and then you can just plot the free energy, so just trace of E minus beta H, and you have exactly the same type of thing. So for the real part, you see here, even though, so this is for a fixed relation of the coupling, you see like you have this, the same pattern, but a bit more wiggly here. And what's interesting is that the imaginary part also have this saw-like pattern. And this is evidence that this half-wormhole is also there in SYK. And so one way to understand this, to give you some intuition, is as follows. So I'm not giving the exact formulas, but they can be found in the paper. Like the point is, there are two saddle points, so the partition function can be written as a sum of so this is the black hole contribution, which is approximately constant, and there is also this half-wormhole has approximately this behavior, so there's a phase in 1 over t. And since the imaginary part of f is the argument of this z, you can see that for S1 bigger than S0, what you have is, you know, as t will vary, like this phase will change, and you have that z will, basically z will, so z is a point in the convex plane that will circle around the origin, and then because of this argument, you have this distinctive saw pattern in imaginary part of f. And the fact that we see it in SYK, so this is just by numerically doing this computation, shows that, you know, in SYK, the simplest explanation is that this additional saddle point is there, and this is exactly the half-wormhole. So yes, so I think, of course, this is qualitative, and it's hard to be quantitative here because we are doing SYK at a fixed relation of the coupling. But I think this is good evidence that this half-wormhole is also there in SYK. And there is a slightly quantitative thing that we can do, which is that so J of tau has many Fourier modes, and this corresponds to all this complication you can have. But in particular, the zero mode, the zero mode corresponds to basically the number of oscillations you will have here. And in SYK, what corresponds to this is the center of mass of the coupling. So if you have a fixed choice of this J and N, you can do the center of mass, which is just your sum over all AJKL and divided by the number of terms. And this Z is basically the same role of J0. So in some sense, they are dual to each other. So this is interesting because you can see really that some features of this boundary condition J of top correspond to some features of this coupling GIJK. And yeah, so just to say, like using the gravity picture, then you even get an analytical formula for this imaginary part that does matches quite well with SYK. So yeah, just to summarize this half-wormhole story, like using this duality between complexified SYK and JT with a massless scalar, you have a model where you can really solve the factorization problem and see how it's solved in terms of half-wormhole. And so here is a non-average theory corresponds to the theory with half-wormhole, and the average theory is the theory where you average over this boundary condition, which gives the gravity with wormhole. And again, this idea should generalize to higher dimensions simply because it corresponds to doing the path integral in some specific order. And it seems that for any time you have a wormhole saddle point, you should be able to do this and split it into two half-wormhole. And so I think it would be interesting to look at this in higher dimension also. Yeah, so in the last 20 minutes, I want to talk about something slightly different. So if there's any question about this part, feel free to ask. Yeah, okay. So now let me talk about another thing you can do with this model, which is related to, okay, maybe the motivation for this is to understand better the choice of contour in the gravity path integral. So here, the point is that it is rather unclear what geometry have to be included and how to choose this integration contour. And so here, in our model, we will see that there's a nice phenomena that happens where we can study this. And the idea here is that by adding some interside coupling, there is some interesting transition that we observe. And this transition can only be reproduced in JT gravity if there is a specific change of contour that happens. And so, this gives a way to, this gives a situation where you know what the contour should be at least. So let me explain this in more detail. So the first thing that we'll do is to add, in addition to this imaginary source, we will add explicit coupling between the two sides. So this is a double trace deformation that was first proposed by Godet and in this context by Malesna and Chi. And if you just add this type of double trace deformation between two SYK or between the two boundaries of ADS2, this allows you to get an external traversable wormhole. And this gives a wormhole that has similar thermodynamic property as the one we studied. And the geometry, so in this case, it has a Lorentzian interpretation, and it's just the global ADS2 geometry. And so what we want to do here is to have the model we have, so the complexified SYK model. But in addition, we also add this coupling between the two sides. So now we have a model with two parameters, k and eta. So indeed, this model can be studied in the same way using Schwarzenberg equations and numerical diagonalization. And on the JT side, we have this massless scalar field and also some coupling between operators on two sides, as was studied by Malesna and Ki. And so this gives a slightly more complicated model that has, and so it has, you can solve the saddle, you can find the saddle point of this model, and it's a bit more intricate. So there are three more wormhole solutions given by a solution of a cubic equation. Okay, so let me just, you can test the duality a bit more by computing physical quantity on both sides. For example, the energy gap in the wormhole phase, this energy gap has some nice analytic formula in the JT side, and you can just compare it the SYK side and see that it does match quite well. But actually, the interesting thing here is that if you increase this interside coupling beyond some value at fixed k, there is an interesting transition where the energetic spectrum goes from complex to real. So here we are studying a non-Hermitian system where the Hamiltonian has complex eigenvalues. But this is fine because we are just interested in the thermodynamics property, basically studying trace E minus beta h. And we can think of it as some analytically continuous partial function. So in general, we expect the eigenvalues to be complex. But what is interesting is if you increase eta beyond some values, the eigenvalues become real in a rather non-trivial way. And this you can check by computing some order parameter, which is basically just the derivative of the log z with respect to k. And this is basically the imaginary part, the expression value of the imaginary part of the Hamiltonian. But what you see in SYK is that you have some non-trivial value here. We have, but beyond some lambda is the same as eta. It becomes zero abruptly. And you can just see explicitly that the spectrum is real there. And so in JT gravity, there is a nice way to interpret this transition actually as a restoration of the symmetry. So the idea here is that there are two geometries that you can consider. So the global ADS2 geometry has a full SL2R symmetry, but in the Euclidean wormhole, when you identify the time, you get only a U1 symmetry. And this transition can actually be understood as a restoration of the SL2R symmetry, which is broken to U1 in the Euclidean wormhole. And what happens is, once you restore the symmetry, then the spectrum has to be real, because the system does have a Lorentzian interpretation. And so this is what explains also this complex to real transition. And you can also show that once you have this SL2R symmetry, this quantity has to be zero. So there is also the sharp transition that you see in JT gravity. But yeah, and another thing that is interesting here is that the Hamiltonian is still non-Hermitian above the transition because k is non-zero. But the eigenvalues are real, and so this is this gives a theory that also has a Lorentzian description. So it's what is known as pseudo-Hermitian quantum mechanics. And so one famous example of this is PT symmetric quantum mechanics, where you have a non-Hermitian Hamiltonian, which still defines a good quantum mechanical theory. And so here, the only difference here is that to define, so you have a good quantum mechanical theory with unitary evolution, but you just need to modify the inner product here. So on the JT side, the way to understand this transition is as a change of contour. So okay, I didn't give the detail of this analysis, but just to give some detail, in this model, the path integral takes this form. So you have the black hole saddle point, and the wormhole saddle point can actually be written as a path integral, as an integral of a single real variable, where the action is like a quartic polynomial. And so here you can see that there are three wormhole saddle points, which are solutions to this cubic equation. And in general, yeah, so what happens above the transition is that two of these saddle points become complex. And then you can think of what contour you should choose for this path integral. And the transition can be understood, can be explained by the change of such contour. So it's not clear, yeah, I must say it's not clear what is the gravitational mechanism that implies that such change of contour, have to take place in the gravity side. But the fact that we have this microscopic SYK description shows us that this change of contour has to take place. And one thing that would work, for example, if you change from x positive to the x positive contour to the x negative contour. And okay, there's another observable that you can compare with the two sides, just to say, like, like the phase shift between the green function, the left-left and left-right green function, is also an order parameter for this transition. And both in SYK and JT, also they give exactly the same behavior. So this is another check of this duality. Okay, so I hope it was not too fast. Actually, let me now conclude. So basically, we have studied the SYK model with complex coupling and proposed that its dual is JT gravity, where you have complex sources for a massless scalar. And this gives a simple time model where wormhole effects in the path integral can be studied. And so we have given example of 3 of these effects. So the first one was this Euclidean wormhole solution and this thermal phase transition between a wormhole and 2 black holes. Another thing we can study is the Factorization Puzzle and the average by constructing these half-wormhole saddle points. And finally, we can study the contour in the path integral by this interesting phenomena of this Euclidean-to-Lorentzian transition. And everything we did was done using tools that should be available in higher dimensions, such, just add sources, boundary sources, and look for saddle points. And so hopefully we'll be able to generalize some of these results to higher dimensional ADS-CFT.